Nice, thank you. So I'm sorry for a little bit for the title, and it's pretty long. It's a long title with a tagline, so I will explain a little bit deeper what is it. So thankfully, I can skip a little bit the introduction because the goal of my thesis is to develop some instrumentation and apparatus based on the NV Center to probe some spin waves. At the beginning, I want to just summarize as quick as possible what is an NV Center and properties. But I think most of the people already know what is it, because we are one of the most specialized companies in the world here in this city. And so NV Center is a defect on the carbon lattice of a diamond. Two carbon are substituted by one nitrogen and one vacancy, plus an electron. And this atomic defect has some optical properties. It's basically a fluorescence defect. You can shine with a green laser and you have some emission of light on the red spectrum. And if you go a little bit deeper of the NV properties, but I will skip because now it's a bit late. But you can manipulate optically and with a microwave frequency the spin states of the NV Center. And thanks to this manipulation, you can probe the magnetic field around the NV Center by looking the fluorescence dependency over versus the radio wave frequency of your microwave. And if you couple that to some scanning probes, microscopy techniques, so basically you take an AFM probe made in diamond with an NV at the end of the tips, and you scan your sample, you have some confocal setup. So this is the confocal setup. So now it's not working again. See, okay, this is the confocal setup. You have to focus on the NV tips, your laser for the excitation. You have to collect the light emitted by the NV from the same optical path, and you can move your sample below it to scan. So you can do this kind of measurement scanning. It's a microscopic scanning of magnetic field or some quantitative measurements. So now the presentation itself. I will start a little bit by the motivation of this project, and after that, I will explain what is basically the journey to achieve this kind of measurement. So first, we want to probe spin waves in YIG. YIG is material, it's yttrium iron garnet. And the spin wave, basically, it's you have your sample here. You apply an external magnetic field orthogonal to your sample plane. You put all the spin of your sample in the same direction, and you put off equilibrium, and you have some propagating wave like this on your sample. And the idea is not to studying propagating wave, but to studying some resonant mode on the YIG disk. So here you have an example of a YIG disk with an Kittel mode. So all the spin process in phase. And by some kind of measurement, basically we can do some relaxometry. This means you have a spin of your sample which process at a certain frequency. And if this frequency match the Larmor frequency of your NV Center, you have a dissipation canal between them. And the lifetime of the NV will decrease. So the extension peak, as I explained at the beginning, will be more broader. So you can probe like this some spin wave oscillation. But not just that, the title of this presentation is hidden mode and spin wave, because you can have some mode, resonance mode on disk, where locally the spin process out of phase. And if you look the spatial integration of this precession, it's equal to 0. So to probe these kind of things, you need a very high spatial resolution given by the SPM techniques with NV. But what we want to do is spin wave in YIG, yttrium iron garnet. And the YIG have very, very low damping factor, magnetic damping factor. It means that the Q factor, the resonance factor of the YIG is very high. So the resonance peak is very narrow. And this induces the fact of we have to apply a very, very well-defined and well-stable field to our sample. So this is the beginning of the journey, in fact, because we want very stable field. So our technical choice to achieve that is to use an electromagnet. It's an inductive magnet, relatively large one with one diameter coil, And to achieve high stability, we use a closed loop system. Here you can see, and the little white part, this is an NMR sensor, nuclear magnetic resonance sensor. And this gives the ability to this system to have a closed loop to control the power supply and to achieve a magnetic field at the ppm resolution, so 10⁻⁶ resolution. But this at the cost of the space we have to fit our microscope. So basically, our microscope is this tube, and because we want to well control also the orientation of the magnetic field, we choose to the possibility to we let the possibility to turn the magnet, to turn the orientation field. So the idea is to be able to turn the magnet along his vertical axis. So the microscope should be fit on the 10 centimeter air gap of the magnet, but it should be also a tube because we can make some rotation around it. And this creates constraint because if you look on the current state of the microscope now, so this is the microscope now today, there are lots of things inside, a lot of actuation because it's SPM techniques and it's so you have to move the sample, you have thermal regulation. So it's worked at ambient pressure and also at room temperature. But something is missing now in this picture is the optics. In fact, we have no the optics, still no optics now. And this representation here is a 3D representation of this setup with something hidden. And here you can see something called l'Arctic objective, and this is the next point, in fact. Because at this state, we need to very strange this fake laser pointer. It's a little bit dark on this screen, but here you can see a side picture of a cantilever with NV tips at the end. And here you have a loop. This is a microwave antenna. And just to give you some indication of the size, the diameter of this wire, it's more or less 15 micrometer. So it means we have not so much space to fit the optics, but we have to achieve a very good position of the NV center compared to the optics. Here, this is an overview. In this case, it's on axis, on optical axis. It's a scanning fluorescent view. So here you have the tips. It's basically on the range, the size is on the micrometer, but you have to find the tips, but you have also to find the NV center on the tips and to maintain the position of the focal objective compared to the position of the NV. So it's pretty tricky. So at this point, we say, okay, we have to just to fit in our microscope some confocal techniques. So it's not a big deal, but in fact, yes, because the first study was to just use the same objective we use on a tabletop setup and just put optical fiber for incoming laser and for outcoming fluorescence beam. So if we follow the path, we have optical fiber here with a laser coming inside the microscope. We collimate to the infinite the laser beam. It will pass here a bandpass filter. It's a dichroic mirror. It will be focused on the NV center by this objective. The light emitted by the NV will be collected through the same optical path, reflected by this bandpass filter, dichroic mirror, and collimated, focused into optical fiber. But at this point, something very important is the fact of the wavelengths of excitation and wavelength of fluorescence are very different. So you need a very good objective to achieve this kind of setup, of confocal setup. And standard objectives are refractive objective, and it's based on lens. And to achieve good, not perfect, but good achromaticity, it means achromaticity, it means the length distance, the focal length distance will not depend on the wavelength of the beam. And to achieve that, the company used lots of lens inside their objective to compensate the achromaticity of all the lens by overlens. And the cost of this choice is the length of your objective, the aspect ratio, the diameter of the objective compared to the length of the objective. And if you look for good objective, the length is almost never below 50 nanometer. And we don't have 50 millimeter, sorry. And we don't have 50 millimeter. And if you say, okay, maybe we can use not so good lens, in fact, it's impossible. We will not collect the light at the same point of focus your laser. So it's not a good idea. So we search for some solution. It exists, and some solution perfectly achromatic. In this case, we don't use a refractive lens. We don't use a lens. We use mirror like a telescope. And this is a standard product. It's called Schwarzschild objective. It's based on conjugation of parabola and ellipse. This is a cut view of this kind of system. It's pretty nice because the length is pretty low, and it's perfectly achromatic in terms of the focal length. But you see here there are two mirrors, primary mirror here and secondary here. And the first mirror is exactly at the center of the field of view of the objective. And if you look, so this is create a blind spot, in fact, obscuration at the field of the center of the field of view. And see, if you look the fluorescence dependency of an cantilever in the center, it's exactly where is the maximum of the light of the signal. So it's pretty no-go to use this kind of thing. And now we can pass to our custom-made development for that. So the idea here, so this is a cut view mathematical representation of what we design. So we still use reflective system, so perfectly achromatic. We still use a conjunction of parabola and ellipse, but in this case, and with axis of rotation, but in this case, we develop something without a blind spot at the middle. So here you have an axis of revolution. This is the optical axis in purple. And we will just look at the right part. It's exactly the same. You have symmetry. And here I let the description of the first reflective surface in red. This is an ellipse with two focal points. One focal point is basically the focal point of the objective. So you are in the center. And the second focal point is here, the second focal point of the ellipse. So the light emitted in the center will be reflected by this first surface, focus in direction of this second focal point. But before it's completely focused, it will be reflected again by a second surface, which is a parabola with the same focal point, so collimated to the infinite. After that, you have two other surfaces just to put the beam on the axis. So, okay, this is the mathematical description of our system. Okay, on paper it's work. It's purely simulation, ray tracing simulation. Okay, maybe it's good. The size seems to be good. It's below 30 meters in diameter, and it's less than 1.5 centimeters long. So we keep this idea, and we try to see if it's possible to implement this in the real world. And it seems it's possible. Pretty hard, extremely hard, but it seems it's possible. So the idea here, now you have a cut view of our prototype design with a superposition of mathematical definition of the surface. So here, again, you have four reflective surfaces. The ellipse here, the parabola here, and two linear here. And how we can achieve a reflection? We don't use metallic mirror like a telescope, but we use total internal reflection between, the physical principle of reflection between at the interface between two optical medium with different refractive index. In fact, it's a prism. This is the principle of a prism. So in this design, you have air or vacuum around. In blue, you have optical polymer. It's basically super close to the polymer of my glasses. And on the center, you have an vacuum area. In fact, it's air or vacuum, and you have a little hole here for the pressure equalization. So the light will enter into the objective here. This is a sphere with the center at exactly the focal point of the objective. And after that, it will be reflected by the ellipse, the parabola, and two linear surfaces. So this design is great because we ensure that at each point of the interested beam, we are in the condition of total internal reflection. Because it's an angular condition, you have to be to have an angle bigger than the critical angle. And with this design, we have something purely achromatic, optimized for confocal microscopy or spectroscopy, compact, with enough space to integrate the NV sensor and the antenna, and with high numerical aperture. So now I will stop about this subject now because we still doing some development, and we're waiting, in fact, for the delivering of the first prototype by a company who can achieve this kind of manufacturing. And just to conclude this, well, it's not fair because this is an objective for direct imaging microscopy, but it's commonly used for NV setup. And this is a comparison with our design. It's purely confocal design, but should be with the same performances for NV. And now speaking about the other part of the project. So we're waiting for the delivering of the microscope objective now. And we cannot just wait and wait and wait. We have to develop the other part of the microscope. So here you have, in fact, a second setup on table, an optical table. And we have three main parts: the laser pulse box for where is generate the laser and where we can generate laser pulse, the detection box, basically it's just avalanche photodiode, and then replica of the microscope inside the tube, but on optical table, without the constraint of the size or of volume. Basically, the first two boxes will stay the same for the final setup. We just have to put some optical fiber to come out the laser and to put the fluorescence here. If we just see another point of view from the top, we found the same elements. So microscope objective, the laser comes from here, and the fluorescence will go in this direction. You have here an arm with a tuning fork and the NV at the end, antenna in front of it, and here, well, it's a piece of paper here, but the sample holder for the scanning. And speaking about how we choose to manage this kind of project, we want something as tunable as possible. So we choose to develop not to develop, but to be as flexible as possible for all the systems. So for example, the AFM part, purely speaking about the AFM part, it's unmade. So we use a DAC just to generate XYZ position we want for the scanning. And we use the HF2LE from Zurich Instruments for the retroaction and for the feedback of the distance between the cantilever, the AFM tips, and the sample. So you have to, and we use the correction from the PID of the lock-in as an order to decrease or increase the distance between the tips and the AFM. So you have to develop some things like transimpedance amplifier. It's detailed, and summing amplifier, but it's not a big deal. And speaking about the NV protocol itself, we also choose to develop something custom made. So for the timing, we use HDLW G from Zurich again to generate precise timing and synchronization for all the instrumentation. So here we have a model with 4 channels, but in fact we can use 8 as an 8 triggering sequencer. You have 4 main wave output, but also mark trigger output. So with this, you can trigger microwave generator, you can trigger a microwave switch, acoustic modulator to make laser pulse, and you can also trigger some measurements, timing measurement, and for that we use a Swaben instrument time tagger. You can achieve a very good timing resolution. And just to finish this part, this is the first imaging we had with our table setup last week or the week before. So, okay, it's purely raw data without any kind of post-processing. So here you have the AFM part. So the topography of the sample. So we well see the tilt of the sample and the thermal drift over the time. And here you have corresponding fluorescence scanning of the NV. So it means at each point we see the topography and we measure at the same time the fluorescence of the NV center through the confocal setup. And you can probe like this by quenching or diminution of fluorescence, some magnetic texture. And just to finish, this is also something not well understood. It's just to test if we see something. In fact, at this point, it's purely just test of the setup. This is part of the hard drive, and same idea. We have a first version over the position of the NV center. So the size here, it's a 5 by 5 micron, and the same for the previous one. So if I summarize, in this project, it's complicated. We want to achieve some kind of measurements, but we have to develop some new tools, but we have to develop also some customable way of measuring. And we're still waiting for final setup, the delivering of the objective. And here, just a little bit of advertising for Hugo. He's on the Netherlands Institute, so we have the same responsible. And here, very, very nice poster. We're doing crazy things like vectorial AFM with a silicon carbine nanowire.